Good morning, boys and girls, and welcome to Derivatives as Rates of Change. This should be a fun one for you if you are a physics person. All my physics kids, I think you've dealt a lot with this, the ideas we're going to cover in this unit before, already in physics, so it should be a quick little kind of refresher. And if you're not in physics, this is a fun way we can apply a lot of the topics that we are talking about in calculus to something a little bit more practical. All right, so let's start out here. Given a particle in motion, its position can be described by using the function. Maybe I should put the function there. For us in calculus, we will generally use S of t to talk about the position of a function. Sometimes you will see, and in physics, I believe you guys use more x of t. But both of these are functions that we use to describe position. For us, again, mainly we are going to use S of t. I think you see that one way more often in calculus. Okay, x of t is more of a physics thing, but it does pop up from time to time. All right. With that being said, now, if I'm talking about a position function of an object, we have talked about, we started early on. We talked about a position function, right? With its position with respect to time. And we talked about how, hey, if I were to look at the slope of the secant line, right, that is the average rate of change or the average velocity of the object. Okay. So this is, again, given, that's its position, that's the time, the independent variable is the time, and then up here is the, is the position, right? This is S of t. The average rate of change is the slope of the secant line. Average rate of change, or average velocity. All right. And then we also talked about, very similarly, given that same function, right, that if we look at the slope of the, I guess the way I'm drawing this may not make a ton of sense, but if I look at the slope of the tangent line, or the derivative, right, so the tangent line is the derivative at a point, right, this would give us the instantaneous rate of change, or the instantaneous velocity. Okay, so quick little review there. The slope of the secant line, S of b minus f of a over b minus a, right? Just our slope formula is the average rate of change or the average velocity. The slope of the tangent line, the derivative, S prime, is your instantaneous rate of change or the instantaneous velocity. Okay, so with that being said, the velocity of a particle in motion is equal to the derivative of its position. Okay, because the derivative is equal to the instantaneous rate of change, or the slope of the tangent line, or the velocity. Again, you want these terms, the reason I keep saying them, is you want those terms synonymous in your head. Okay, the derivative, instantaneous rate of change, velocity in this case, okay, those all are talking about the same thing. And then, I guess if we took it a step further, another thing we should know then is the acceleration of an object is the rate of change in which the velocity is changing. So the acceleration is the derivative of velocity, which is the second derivative of position. Okay, so we want to be familiar that with these kind of basic concepts, velocity is the derivative of position, and the acceleration is the second derivative of position, or the derivative of velocity. All right. Then, also, just by the way, we're setting movement up by convention. Okay. If my velocity is greater than 0, if the velocity is positive, velocity is like an amount, but it also indicates a direction. Okay, if the velocity is positive, that is telling me I am moving. Ooh, that's not how you spell moving. Oh boy. Moving to the right, or up, or forward. Okay, if your velocity is positive, that indicates that you're moving to the right, you're moving up, or you're moving forward. Similarly, by convention, if the velocity is negative, if it is less than 0, it is moving to the left, or down, or backward, depending which direction we're talking about. I guess that means that if my velocity equals 0, I'm stopped. I'm not moving anywhere, right? Maybe that goes without saying, but that means I'm going to be stopped. Okay? But when we talk about velocity, velocity has like two components to it. It's got magnitude, how fast you're actually moving, and it's got a direction vector associated with it, either right or left, up or down, forward or backward. Okay? If I'm just looking for the magnitude part of that, how fast something's going, and not with the direction associated with it, that's what we refer to as speed. Okay, and so speed is the absolute value of velocity. So speed and velocity are very similar, but slightly different. I talk about my speed going down the freeway. I'm going 60 miles an hour. You just know how fast I'm going. You don't know in which direction I am traveling. Okay, so speed is the absolute value of velocity. It is the magnitude without the direction associated with it. Okay, and then I guess we know then with all this that an object, maybe this kind of goes without saying, but an object changes direction, then changes direction when velocity changes sign. Ah! Things are disappearing on me again. What's happening? Oh no! Okay, it's back. I realize one thing here. I realize I'm doing a lot of writing as I'm talking here. Changes sign. And I thought, man, I should have probably stopped that. And then as I did that again, I must hit a button on the pen, and it makes it like just all disappear. All right. But anyway, so I know that objects are going to change direction when the velocity changes sign. Again, if it's positive, it's moving to the right. Then if it's negative, it's moving to the left. So when my velocity changes sign, I know the object has to change direction. Okay, so let's kind of play around with this just a little bit here. So here is the position function for an object moving along the x-axis, okay, moving horizontally at any time given t. Okay, so if I wanted to play around with this and kind of learn about what's going on, I could take the derivative of this. If I took the derivative of the position, then I'm finding the velocity of that function. If I take the derivative of 3 times this, I'm going to end up with just t squared. If I take the derivative of that, multiply by 2, I get minus 3t. Take the derivative of that, I get plus 2. The derivative constant is 0. So that works out rather nicely for us. The position was kind of ugly, but the velocity or the derivative is a little bit cleaner. I could take this now and factor it. T minus 1, t minus 2, and set that equal to 0. The reason I would do that is now I'm finding out where this is stopped. Okay, so this is obviously stopped at t equals 1 and t equals 2. I could chart this stuff on a number line. 1, 2, that's where it's going to be stopped. And I can plug in values that are in between. Like let's say if I plug in, if I plug in 0 to this. And again, I can plug in right here. I really just care about signs. 0 minus 1 is a negative. 0 minus 2 is also a negative. So a negative times a negative is a positive. So over here, that means I'm going to be moving to the right. Between 1 and 2, if I plugged in a number bigger than 1 but smaller than 2, like 3/2, I would get a positive here when I plug in 3/2 times a negative here. So that would be negative. And then if I plug in a number bigger than 2, like 7, I'd get a positive times a positive. So that'd be positive. So I know like this particle is going to move to the right. If I'm going t greater than 0, it's moving to the right to 1. At 1, it stops for a second. Stops. And then from 1 to 2, it's going to move, back to the left. And again, I don't know how far it's actually moving. I just know the direction it's going. And then from 2 onwards, it's moving back to the right. Okay? So that's what I can kind of tell by looking at the velocity function. If I wanted to, I could even go and look at the acceleration of this. Acceleration is the derivative of velocity. So my acceleration is the derivative of velocity, or the second derivative of position. And so that would give me 2t minus 3 And I could set this equal to 0 as well, and I would get, oh, you know, this is going to happen at t equals 3/2. Okay? The green was our velocity. The black is our acceleration. I'm going to do another number line above it. And again, I could put something in that was smaller than 3/2, like 0, and if I put in 0, I'd get a negative, and if I put in something bigger than 0, I'd get or bigger than 3/2, like 5, I would get a positive. So this means I'm accelerating to the left for all values less than 3/2, and I'm accelerating to the right for all values greater than 3/2. Okay. Oh, probably something we should talk about here. So, if we want to talk about like speeding up or slowing down. Okay, I am speeding up when the acceleration and velocity have the same signs. Okay? Or I'm slowing down when they have different signs. If I look here, if the acceleration, my velocity from 0 to 1 is positive, but my acceleration is negative, that means I'm slowing down on 0 to 1. Does that make sense? Then from 1 to 3/2, they're both negative. So I'm speeding up to the left because I'm accelerating to the left and going to the left. So I'm actually speeding up in that direction. Okay? Then from 3/2 to 2, again, because the signs are different, I am now slowing down. I am going to the left, but accelerating to the right. And then from 2 onwards, I'm going right. I stop at 2, and then, from 2 onwards, I'm going right, and I'm accelerating right, so I'd be speeding up to the right. Okay? So that's how you can kind of use those in conjunction to see what an object is doing. Okay, next example here. Suppose a stone is thrown vertically upward from the edge of a cliff on Mars, where the acceleration due to gravity is only about 12 feet per second squared, with an initial velocity of 64 feet per second from a height of 192 feet above the ground. The height s of the stone above the ground after t seconds is given by the following function. S equals negative 6t squared plus 64t plus 192. Okay? So we got a stone being thrown on Mars. This is the function that represents the throw. Part A, we want to just find the velocity of the stone at any time t. Well, if we want velocity, velocity is the derivative of position, so that'd be negative 12t plus 64. When you write this stuff out, again, I think this is good notation here, okay? Tell people when you're finding the velocity that is the derivative of position, and then you can actually go and do it. But you're communicating how you are getting the velocity when you write it like that. Okay, part B. We want to know when the stone reaches its highest point. So if the stone goes up, and then it comes back down, it's going to have to stop somewhere, right? So I'd want to find out when it's at its highest point, I'd want to take my velocity and set it equal to 0. And I could go and solve this equation, and if I do that, I get negative 12t equals negative 64, or I get t equals, if I divide by 12, negative 12, 16 over 3. Okay, that's when the velocity stops, and therefore when it's at its highest point. Part C says, so what is the height at the highest point? Well, if I want the height at the highest point, I'm going to take this time, and I'm going to plug it into the position function. And this part, I would say you could just go ahead and probably evaluate that on your calculator. Okay, I'm not sure if I've showed this to you, but what I can do with this too is I can put the position function in my calculator in y1, and then now I can come here and go alpha trace y1, and I can just do, like I do f of 3, 16. Oh, it's going slow. 16. I can do 16 divided by 3 and enter it just like that, and the calculator will kick out our answer. Oh, so its position is 362.6667 feet. All right, thanks, boys and girls, and I will talk to you later. Bye.